I recently had the great opportunity to address the ICC Region 8 group, and we discussed ceiling grid installations, and they asked me to provide them with a copy of that PowerPoint presentation. So that's what we're going to provide here today. So we hope this information is helpful to you, and we hope that you like and subscribe. So let's get started. I'm constantly amazed at the inspectors that don't even realize that suspended acoustical ceilings are covered in the code. You actually go to usually the last part of Chapter 8, and we're referencing the 2021 IBC. I'll have a link to the IBC in the description where you can purchase a copy of this book along with some others. The ASTM standards, you'll have to get those from ASTM. We cannot, because of copyright issues, cannot post those. But here's what our code says. 808.1.1.1, suspended acoustical ceilings. Now, some say ACT ceilings, some say drop ceilings. I think we all know what we're talking about. Suspended acoustical ceiling systems shall be installed in accordance with the provisions of ASTM C635 and ASTM C636. Now, ASTM C635 covers mainly the mechanics as far as the thickness of the metal and the finishes, the coatings, and all that kind of stuff. It's the ASTM C636 that we need to look at strongly for the inspection purposes of this program. We should also be referencing Chapter 16 of the IBC, and again, we're in the 2021 edition. For earthquake loads, every structure and portion thereof, including non-structural components. Now, non-structural components are your suspended ceilings that are permanently attached to structures, and their supports and attachments shall be designed and constructed to resist the effects of earthquake motions in accordance with ASCE 7, excluding Chapter 14 and Appendix 11A. The seismic design category for a structure is permitted to be determined in accordance with Section 1613 or ASCE 7. Now, the addition of ASCE 7 is referenced in your code book, so whichever code book you have will give you the current edition of ASCE you need to look at, and you'll be looking at Chapter 13, just a brief couple of paragraphs there in 13. And of course, there's always exceptions in anything in the code, right? So detached one or two family dwellings pretty much are excluded. Wood frame buildings that conform to provisions of 2308 not required. Agricultural buildings, structures that require special consideration, such as transmission towers, hydraulic structures, and that nature. We must also look at the other materials in 2506 of the building code, and it's going to tell you that metal suspension systems for acoustical and lay-in panel set tiles must conform to ASTM 635, which we covered, listed in Chapter 35 and Section 13.5.6 of ASCE 7. And this is for high seismic areas. So don't go thinking this doesn't apply to you, because the seismic code changes have occurred in the last couple of cycles. In the past, seismic force levels were only considered in certain earthquake-prone locations, but major revisions in the IBC have changed these requirements, and now they mandate that every construction project must include and meet seismic design category determinations, even locations that typically don't have seismic events in the past. Now, I'm located in South Carolina, the southeastern United States. Most people think when they think of South Carolina, they think about Charleston and earthquakes down there, and that's true. But we also, in the upstate where I live, up toward Greenville, Spartanburg area in South Carolina, we have quite often quite a lot of activity going on. I suggest you go to the U.S. Geological site and look in your area and see about what kind of activity is going on. You will be extremely surprised. And this earth is moving, and so it's something to be considered. You can look right here in the southeastern United States and see just in South Carolina, North Carolina, Georgia, and Tennessee some recent activity that occurred in August of 2025. This was 1 month. Now look at the ones that were magnitude 2.5. That's kind of the break line. Usually anything less than 2.5, you don't even feel it, but after that you can kind of feel the earth moving. So again, a magnitude 2.5 earthquake will typically not cause any structural damage. It may not even be felt by a lot of people. But though that's the fact that still some minor damage to glassware or other fragile items is possible. So structural damage to buildings generally does not begin to occur until magnitude 5.5 and above. A major earthquake is usually 8.0 or greater. 6.0 to 7.9 is a strong earthquake and can cause serious damage. 5.5 to 5.9 is typically considered moderate earthquake. So let's start seeing how the building code kind of determines to what degree a building must comply with certain requirements, especially for seismic activity. We have occupancy categories 1 through 4 that are established in the building code. Occupancy category 1, of course, is low hazard. That's usually going to be, agricultural buildings, things like that. The really big ones that you need to look at is 3 and 4. 3 are substantial hazard to human life events. These are your schools, jails, buildings with public assembly areas containing greater than 300 occupants, like your assembly halls. But category 4 are your essential facilities. This is your hospitals, police, fire, and rescue stations, designated emergency shelters, and critical national defense facilities. A lot of people just naturally think of the hospital, but they don't realize that the police department and the fire department also are considered essential facilities and are classified as occupancy category 4. The importance factor is determined from design loads of buildings and other structures, and again, you're going to the ASCE 7, and it's based on the occupancy category. It's utilized to calculate flood, wind, snow, seismic, and even ice design loads. So the importance factor is a multiplier that increases or decreases the base design loads. This is all done by the engineer and should be on the first page of your structural drawings on a set of commercial plans. Typically, the base design loads are outlined by the code as a 2% annual probability of exceeding certain load levels. Therefore, an elevated importance factor creates proportionally higher design loads, which must be factored into the building construction. And again, all this work is done by the structural engineer. And we see here that all these factors come into not only earthquake, but also your snow and wind loads. Another factor that comes into play for the structural engineer is the soil conditions. This is done after an analysis by typically a third-party inspection agency that goes out and does an analysis of the soil where the building's going to be located. So the soil conditions come into play, the building usage, and also its geographic location. The determination by the independent testing group as to what the soil conditions are can have a major impact on how the design of the building is and also in cost. Different categories of soil conditions are listed A through F typically. A being hard rock, B being rock, C is dense soil with soft rock, D is a stiff soil, and D is the default category. A lot of times if the location is inconclusive as far as the testing, then it's just done as a default in D. And of course, E is your soft soils and your F is your special soils. So when we get into E and F, we're talking about, mainly coastal regions and areas like that. Again, a determining factor is the building usage, right? So seismic use 1 is pretty much everything that's not in 2 and 3, right? Seismic 2 is buildings that constitute a substantial public hazard, and 3 are your essential facilities, which we covered in an earlier slide. And obviously, geographic location is a factor. California is not the only region considered at risk for seismic activity. There's been more than 3,500 earthquakes have been recorded east of the Mississippi River since 1700. And of course, the biggest one that a lot of people know about is Charleston, South Carolina. By analyzing these 3 criteria that we've just been talking about for the construction project, you can determine the seismic design category. It's going to be A through F. This is typically done by the project structural engineer. The seismic design category must be established by a licensed professional engineer, and this should also be based on the ASCE 7. We're going to have a link to where you can purchase both the ICC building code and also the ASC 7 books. Also, I'll have a link where you can go onto the ASTM site and purchase various standards from them. Note, seismic design categories are determined for the entire building. This is why the seismic design category information is on the structural drawings. You can't break a building in two. I've seen one set of plans we had one time where they put a 3-hour firewall up and said because of that they wanted to classify one part of the building C and the other part D, which I found very ridiculous. We sent back, and after the engineer kind of looked it over, he conceded and changed the entire building to a seismic design category D. Jurisdictions using the 2021 IBC follow ASC 710, Section 13.5.6, and ASTM E580, which replaced the CISCA documents. International Building Code allows two paths to determine seismic design categories. That's 1613 or ASC 7. ASC 7 has an entire chapter titled Seismic Design Requirements for Non-Structural Components that's devoted to provisions on seismic bracing of non-structural components. Unfortunately, not a lot of designers are aware of this part of ASC. So what are considered non-structural components? This consists of architectural, mechanical, electrical, and plumbing utilities. Chapter 13 of ASC 7 establishes the minimum design criteria for non-structural components permanently attached to the structure. This consists of furniture, interior partition walls, ceilings, lights, fans, exterior cladding, exterior walls. This list may seem minor compared to structural components, but if these components are not properly secured, they can fall and hurt the occupants or prevent them from escaping during a seismic event. Now, from the FEMA website, we can see several causes of damage, and these are listed as recessed fixtures supported by suspended ceiling without independent safety wires to the structure above, and they can become dislodged and they can fall. Fixtures with proper safety wires may fall from the grid and dangle from the safety wire, but they're not a threat to the occupants, so therefore they're not hindering ingress or egress. Egress by occupants, ingress by emergency personnel. And unless they're secured to a properly braced ceiling grid, relative movement between the light fixture and the ceiling may damage the ceiling finishes, but it won't hurt the people or hinder ingress or egress. Concerning the suspended ceiling systems, there are a couple of exceptions. Suspended ceilings with areas less than or equal to 144 square feet that are surrounded by walls or soffits that are laterally braced to the structure above are exempt. And suspended ceilings constructed of screw or nail attached gypsum board on one level that are surrounded by and connected to walls or soffits that are laterally braced to the structure above are also exempt from these sections of the code. Current codes have effectively replaced the Ceiling and Interior System Association's book called CISCA that was used for many years. This was prior to 2010. So let's look at the seismic design factors. We're going to break this into three groups, A and B, C, and then D, E, and F. These factors are used to evaluate and establish a seismic design category, and the installation of ceilings can be divided into these three tiers. Now, as we proceed from the least restrictive to the greatest restrictive, we have to remember that anything prior that's mentioned has to be done. So we're going to start with our A and B, and they have to be installed to meet the requirements of ASTM C636. There's no additional seismic requirements other than those. And again, this is in the IBC section 808.1.1.1. So we kind of have to chase this down a little bit. So if we go to the 2021 IBC that I'm referencing at section 808, we're going to see suspended acoustical ceilings. It's going to tell us that they have to be, or they shall be, installed per ASTM 635 and 636. Now, when we get into 636, what's going to happen is it's going to then refer us to another ASTM standard if our seismic design category exceeds the A and B designations. So I suppose what we can call the basics of this entire system is going to be, we start with the A and B and the hanger spacing. Space hangers for carrying channels or main runners should be on 4 foot on center. So kind of look at 4 foot blocking. Each suspension wire shall not hang more than 1 6 out of plumb unless a countersloping wire or horizontal brace is provided. Wire hangers have to be a minimum of number 12 gauge galvanized soft annealed mild steel wire. Again, this is in the standard. We have seen what around my part of the country we call baling wire used, and that's not acceptable. Each suspension wire shall not hang more than 1 6 out of plumb, again, as we said, and this is the case whenever you have some kind of interference like ductwork. And as a reminder, the code does require that products have to be installed per the manufacturer's installation instructions or guide. Quite often we'll see in the different products out there, the different proprietary brands, that will have seismic requirements or suspension system requirements that exceed what's in the code. And if that's the case, we have to go with the more restrictive. All the provisions of the manufacturer installation guides or instructions are required to be followed. So we have for seismic design categories A through E some very common requirements. Install carrying channels so they are all level to within an 1/8 inch in 12 feet. Local kinks or bends shall not be made in the hanger wire as a mean to level. Wire loops shall be tightly formed to prevent vertical movement. This is a common code violation. So this is in our standards. It's also in our manufacturer's installation guides. It says insert the hanger wire ends through a wire hole in the T and wrap the wire ends securely around itself with 3 complete turns within 3 inches. Ensure the remaining wire end is secured so it does not interfere with the placement of ceiling panels. Now there's a twofold process here. So first of all, let's talk about this 3 tight wraps in 3 inches. So we've got to take that number 12 wire and wrap it tightly and then have a complete 3 turns in a 3-inch span. And some say it's difficult to do. It's really not. The other part of this is to ensure the remaining wire end is secured so it does not interfere with placement. Usually what you do is whatever you have, I call it a pigtail. On that pigtail, that wire, you need to turn it up vertical or cut it off. In the code it says it prevents the interference with placement of ceiling panels, but the best thing it does, it prevents you tearing up your arms looking around above ceiling, I think. So here's a really good picture of what we just talked about. We're going to insert the wire through the T, we're going to make it tight, and we're going to have at least 3 tight wraps in 3 inches. And most manufacturers of these T's make no distinction about if you use the square hole or the round hole, as long as you're not using something that interferes with other components of the ceiling grid. And of course, here is an obvious violation. We have, we'll grant them that they might have had a tight wrap at the T there, but you can take my ruler that you see there and you can see in a 3-inch span, there's only about 1 1/2 wraps. So there ought to be 3 tight wraps in 3 inches. There's a purpose to all this. All this has been engineered and it must be installed per the engineering. Again, we're in the basics, right? ASTM 636 says the wire must be wrapped around itself a minimum of 3 full turns within a 3-inch length. And then for safety purposes, the wire must be cut or turned up vertical. So here's the one that's close. We got the 3 tight wraps in 3 inches. We're tightly wrapped around the T. That looks great. But we have that pigtail, is what I call it, just kind of turned up there where it's going to just be kind of hanging out. And it should be cut off close or turned up vertical. This is a good one. So what they did was, they got the tightly attached, and they got 3 tight wraps in 3 inches, and they cut the tail off a little bit there. But why in the world they went through that clip that's supposed to allow movement and the grid to slide is beyond me. So this is incorrect installation. So what we just looked at, we got to make sure that even when we get into our C, D, E, and F seismic design categories, we got to comply with those minimum standards that we see for seismic A and B. So every building in the United States has to have some kind of seismic design category designation. So for that purpose, every building, every commercial building that's built in the United States must meet for a minimum of A and B sections. So now let's move on to seismic C. And remember, everything that applied for A and B still applies here. So ASTM C636, ASTM C635, and ASCE 7 section 1356 direct you to go for seismic C to the installations of ASTM E580. So again, we're kind of having to chase after these different documents, but if there is a document referencing the code, we must go by it, and then if that document that they're referencing also references another document, we continue on that path. So ASTM E580 is for categories C through F. It's the standard practice for installation of ceiling suspension systems for acoustical tile and lay-in panels in areas subject to earthquake ground motions. So now we're in the ASTM E580. Connection devices to supporting construction shall be capable of carrying not less than a 90-pound allowable load. That's the first consideration we have. Following that, each vertical wire shall be attached to the ceiling suspension member and to the support above such that the wire loops tightly wrapped and sharply bent to prevent any vertical movement. The wire must be wrapped around itself a minimum of 3 full turns and 3 inches. You saw this in A and B. This is a very interesting little bit of engineering. If you want to do the math, go right ahead. I welcome you to it. So on the left, you're going to see that large loop, and then on the right, you'll see more of a narrow loop and how it pulls. And so this is the reason why we have to have tight attachment. We don't want a big loop made to the structure or to the ceiling grid below. Suspension wires should not press against ducts or pipes. Now, if you have an obstruction such as ductwork or plumbing or something else in the way, then you have to use counter-sloping wires in the method as you see here from the manufacturer's guide. And these counter splay wires must also be tightly wrapped with 3 tight wraps, the same requirements as we have in the rest of the code. Where an obstruction becomes so great that a trapeze has to be put in place, there are very specific requirements on what the structural components are of that material used for the trapeze. So these are worthwhile of looking at in the code. Let's look at this example we have in this photograph. What we have here is we have some ductwork that is over 4 feet in width, and we also have some sprinkler piping, if you'll see on the right of it. So what they did is they doubled a 1.5 inch cold roll steel, and then they put it up there and made the support from that. So that was an adequate trapeze and met the requirements of the code. So a few highlights here for design category C. We got to have a minimum 7/8 wall molding. The suspension system must not be attached to the wall molding, and it's got to have 3/8 clearance on all sides. And the 3/8 overlap of the suspension systems on the wall molding and the ends of main beams and cross tees must be tied together to prevent their spreading. And safety wires are required on the light fixtures. And we'll cover more of that on the light fixtures when we get to the electrical provisions of the code. So now let's begin to review seismic D, and we're going to go D, and that's probably as far as we're going to go because E and F gets a little bit more technical. It's going to require very, very specific engineering. So for this purpose of this presentation, we're going to be going through seismic D. For seismic D, E, and F, we have to look at both, or all three actually, the building code, which is going to send us to the ASTM 636, which is then going to send us to ASTM E580. So let's look over some of these minimum requirements. We have a minimum of 2-inch wall molding required. The suspension system must be attached to 2 adjacent walls. Opposite walls must have a 3/4 inch clearance. This allows for movement. Ends of main beams and cross tees must be tied together to prevent spreading. Now this can be done by using spreader bars, but more commonly what we see today is proprietary clips. Heavy-duty suspension systems are needed, and the ceiling areas over 1,000 square feet must have horizontal restraint wire or rigid bracing. Ceiling areas over 2,500 square feet must have seismic separation joints or full height partitions. Ceilings without rigid bracing must have 2-inch overside trim rings for sprinklers and for any other penetration. Changes in the ceiling plane must have positive bracing. Cable trays and electrical conduits must be independently supported and braced. Suspended ceilings are subject to special inspection, and the perimeter support wires are required within 8 inches of the wall. So ASCE 7, the 2010 edition, gives you in Chapter 13 the seismic design category D through F requirements. And those are pretty much what we just covered, right? Minimum 2-inch wall molding. We highly recommend you use the ESR reports as provided by ICC. Must be a heavy-duty grid. The grid must be attached to 2 adjacent walls. Must have 3/4 inch clearance. Ends of main beams and cross tees must be tied together to prevent spreading, and the perimeter support wires are required within 8 inches of the wall. In addition, ceiling areas over 1,000 square feet must have horizontal restraint wire or rigid bracing, compression post of what we're talking about. Ceiling areas over 2,500 square feet must have seismic separation joints or full height partitions. Ceilings without grid bracing must have 2-inch oversized rings for sprinklers and other penetrations, or a flex alternative. Changes in ceiling plane must have positive bracing, and cable trays and electrical conduits must be independently supported and braced. And suspended ceilings may be subject to special inspection. This inspector highly recommends that a jurisdiction require special inspection from qualified individuals for suspended ceiling systems. It will make the job of the inspector so much easier. Perimeter support wires are required within 8 inches of the wall. You need to be prepared for this because you're going to get hit with it. They're going to ask, well, what good is the perimeter support wire? So if we look at some of the engineering, we're going to see that in full-scale seismic test evaluations for areas subject to severe seismic motion, the common cause of system failure came from damage to cross-T end connections. Damage occurred in one of 2 ways. Either the connector clip would bend or the base metal bends. When this damage occurs, it allows unbraced sections of ceilings to move up to 3/8 of an inch at each connection. The cumulative effect of damage at the cross-T connection may move the ceiling more than 2 inches. Without the perimeter support wires, test results demonstrate that loads on the ceilings may cause the main beams and the cross-Ts to move beyond the 2-inch wall molding and drop out. System failure then occurs, and it's not going to comply with the code requirements. So here we see a picture of the fixed side connection. You're going to notice that the perimeter support wire is located within 8 inches. You're also going to see that on the fixed side we have a pop rivet holding this in place. Again, we're seeing more and more of the proprietary clips that are allowed as an alternative because they're just not as noticeable as the pop rivets. So on the opposing side, we call that the floating side. We have to have 3/4 of an inch distance from the wall. This allows that grid to travel back and forth. We have to use spreader bars or proprietary clips. You still have to have the perimeter support wire within 8 inches. So again, that perimeter support wire has to maintain the 1 in 6, and I've got some various measurements here on how far that should be, but 1 in 6 is the maximum slope you can have on that counter-sloping wire. Now we saw this slide earlier, but again, I just want to show you for the purpose of what's going on here is this is the floating side using a proprietary clip as we discussed before. And the ideal is this grid will travel 3/4 of an inch. However, when they put that perimeter support wire, even though it's less than 8 inches from the wall, which is good, they ran it through the clip into the T that kind of negated the whole process. So next, let's talk a little bit about this term we heard earlier called compression post. And when we say compression post, we're talking about the horizontal restraint that we have to have that's required by the code. Or more accurately termed the lateral force bracing, the compression post. All right, lateral force bracing is the use of vertical struts, compression posts, and splay wires for ceiling areas that exceed 1,000 square feet. Now, these posts can be a metal stud. I've seen conduit used. They also make proprietary lateral force bracing or compression posts. All these must be reviewed and approved by the building official. And the post must be installed per the engineer's design. Typically on the seismic drawings of the structural set of plans, you're going to have detail about these compression posts. The layout of compression posts and how they start must be detailed on the drawings. In this photograph, we see a metal stud being used for a compression post. Engineering has already been done on a lot of different materials that can be used for compression posts, and you can reference any of these, and that should give you sufficient information to do the inspection. And here's a continuation of the different materials. Some key items to look for on compression posts. Splay wires are to be within 2 inches of the connection of the vertical strut to the suspended ceiling. Rigid bracing may be used in lieu of splay wires. Vertical struts must be positively attached to the suspension system and the structure above. The vertical strut may be EMT conduit, metal studs, or proprietary compression post. In this photograph, we see a compression post, but we don't have any splay wires. Now let's look at seismic separation joints. The standards will require the following. It requires that with suspended ceiling systems that are greater than 2,500 square feet, they must have seismic separation joints, closure angles, and horizontal restraints. This means 2-inch molding, perimeter spacer bars, and if the area is greater than 1,000 square feet, lateral force bracing. So we have to have both. The method of failure was observed during the California earthquakes of the 1980s quite often. And this photograph is an excellent example of a seismic separation joint that was in a hospital I recently inspected. And there are a wide range of proprietary means and materials for creating the seismic separation joint. The separation joint requirement comes from ASC 7, section 13.5.6.2.2. The ceiling area should be divided into sections no greater than 2,500 square feet. It also states that each area is to be provided with the closure angles and the horizontal restraints as prescribed in the same section of the manual. This means 2-inch molding, perimeter spacer bars, and if the area is greater than 1,000 square feet, lateral force bracing. The code does not describe how to construct the seismic separation joint. There are a lot of proprietary clips out there that meet the requirements, and that's typically what's going to be specified on a project. Seismic separation joints are not required when structural analyses are performed on the ceiling bracing system for the prescribed seismic forces that demonstrate ceiling penetrations and closure angles or channels provide sufficient clearance to accommodate an anticipated lateral displacement. So we hear this term bracing and restraint concerning seismic, so let's talk a little bit about this. Attachment to the wall is considered restraint. Bracing is a form of restraint, like a compression post or the wires. So now let's discuss the perimeter molding. Per ASTM E580, unless perimeter members meet the structural load carrying requirements and have been approved as a structural part of the system, wall angles or channels shall be considered as aesthetic closures. In other words, there's no structural value to these, but you've got to check the project specifications on these. Ceiling penetrations. There are specific requirements in ASTM E580 for penetrations of the ceiling system. I think a really good example would be something like a kitchen hood. Typically in a large commercial kitchen, the kitchen hood system is going to be located in the middle of a large room. So then you're going to have a drop ceiling going in or acoustical tile ceiling going in. So how do you handle that around the apron of the kitchen hood? A lot of times you can't connect to the apron itself, so you have to build some kind of a wall there. So the requirements that go around that are very specific and very detailed. Quite often what we recommend is that you get a licensed engineer to come up with a design that you can use for this purpose. So another sometimes tricky operation is when you have what they call clouds and canopies in a structure. Clouds and slope ceilings have specific requirements which should be addressed in the project specifications and prepared by the design engineer. The ASCE Design Manual in Section 13 states that the design of architectural components and their supports is required to meet certain values. So again, an engineer needs to be involved in this process. That engineering will determine many factors, including the distance between a cloud and a wall or an adjacent cloud, and how it should be addressed specific to that seismic design category. Again, if this is being viewed by inspectors, I highly recommend that you defer to an engineer of record. But how much distance is required between canopies? Well, that can be very subjective. You have to look at the different code sections and the ASTM standards and the ASC 7 requirements. This can at times seem a little bit overwhelming, but believe me, it's not that complicated. Again, we need to defer to our engineers of record and defer to the manufacturer's installation instructions. So we touched on this a little bit, but let's get into some of these alternatives that we have available to us today for suspended ceiling systems, installations, and inspections. Instead of spreader bars, typically we're going to see proprietary clips used today. But if they're not used, then spreader bars are still required. Spreader bars are very difficult to keep in place and very cumbersome. So we don't see it as often as we did 10, 15 years ago. There are different evaluation services, and again, many of these are approved for use. ICC has the ESR reports, which I highly recommend. I find that they're very helpful. If you have an iPad or even a phone out in the field, you can look these up very quickly. And quite often, the ESR report is going to be very helpful to you. I have provided this ICC evaluation report for the ESR reports, and here's the website. It's www.icc-es.org. You can go to this site and print out this how to read the report. It'll give you a different breakdown on each and every item. I highly recommend these, and this is something well worth your time to go in and look over. But keep in mind that with the exception of the omission of spreader bars, all other requirements typically are going to have to be met. So manufacturer clips have to be installed exactly as they're detailed in the ESR reports or the product literature. I like the term belt and suspenders. The perimeter clips help you with the stabilization of the entire system, and you got the 8-inch perimeter wire. So between the clips, the 2-inch wall molding, the 8-inch perimeter wires, you kind of got everything covered where the ceiling grid system's not likely to fall, especially in an earthquake of less than significant magnitude, such as an 8.0 or greater. So first, let's look at the ACM7 clips. This is one product that we have out there available, and again, we're not endorsing any products, but these are a couple that I've seen quite often And in this case, you'd go to the ESR 1222. What's really interesting is on these clips, if you look, usually on that clip is stamped the ESR number that you need to look at. And that ESR will give you some very great detail. Now, another comment I want to make on these ESR reports. The code requires that any documents required by the inspector to do their job have to be made available. So if you have a large commercial project, it's not unusual to ask that the ESR report be printed out and made available when you arrive on the site. So let's look at this clip. So on the seismic design category C with a 7/8 inch wall mold detail, of course we got to have 3/8 of an inch on our floating side. So this is the typical installation that we're going to see. And another proprietary clip is the Burke 2 clips. Again, on the clip it'll have stamped which ESR report you want to look at. So you're going to see that ESR 1308 is the one you're going to be looking at here. So again, you got to make sure that you're looking at the right clips and the right ESR reports when you're doing this work. And reading over all the data, you're going to find out that quite often the ESR report is going to coincide with what you've already seen in the code requirements. So here's the ESR report information for Burke 2 clips for seismic design D through F. So let's look at a couple more real-life installations here. So in this case, we have our suspension wires that are just kind of got a very wide loop to the structure above, and the 3 tight wraps and 3 inches just isn't there. We can have a lot of vertical movement, so this would be a no as far as its inspection. I hope you can see this in the photograph. What's interesting about this one is 2 or 3 different things. First, on the lower part at the grid, at the T where you see the wire, you see we just got the wire kind of meandering up, and we also have the clips been bent to try to adjust and level the grid, but we obviously do not have tight attachment and 3 tight wraps and 3 inches on the lower. Same situation to the immediate right where it's attached to the light fixture. Now if you look up to the structure, what you'll see interesting here is they made a loop that went all the way around the structure, and it also included a conduit. So this is a fail by every respect. Again, when you get into certain specialty shadow moldings and ornamental systems, you're going to have the engineering available on the job site in order to conduct your inspection. These installations, again, require very specific manufacturer installation instruction guidelines review, and all this information should be made available to you at the site. So something else we've been seeing a lot lately is these screws that go up into a metal deck above. And there is an ESR report out for these. Remember that in seismic designs D through F, we're going to have 90-pound pull. Also in C, we've got requirements. So we can look at the engineering on this clip. We will find out if we dig into it, these lag type clips do meet the requirements of the code and are acceptable. So now let's discuss the above ceiling or ceiling grid type inspections and how it relates to the electrical systems that we're going to see. You'll see on the photograph to the right a very extreme example of, you'll see the 2x4 troffer lights just kind of laying at the floor. The only thing that's holding them up is the electrical connections, probably MC cable. ASTM 580 in 4.4 reads, all lighting fixtures shall be positively attached to the suspended ceiling system by mechanical means as specified in the National Electric Code unless independently supported. The attachment device shall have the capacity of supporting 100% of the lighting fixture weight acting in any direction, with a minimum of 2 attachment devices required for each fixture. In my area of the Southeast, we've seen a lot of engineers using this design document from the old Cisco books, and they put it on the plans. So therefore, if it's on the plans, that's the way they've got to do it. Here they require that the fixture be positively attached at 4 corners, and also that there be 4 wires put on the light fixture, which is fine. That exceeds code. So let's look at the National Electric Code. NEC 41036 means of support. If we get to the last part, we're going to see that listed clips identified for use with the type of ceiling framing members and luminaires are permitted. The luminaire shall be securely fastened to the ceiling framing member by mechanical means such as bolts, screws, or rivets. That little clip that pops out, that's for aligning the fixture in the grid. That is not the approved UL screw, bolt, or rivet. Now, I have permitted people to use a panhead screw and go through that clip into the ceiling grid, but there are listed clips, and we highly recommend the use of these listed proprietary clips. And this is an excellent example of one of these proprietary clips. So you can see the clip to the right of the suspended suspension wire. That wire is also an engineer design. It's allowed to be equivalent to the number 12, but I'm primarily concerned with the clip in this photograph. And there are many such clips out there on the market. They should be listed. When you look at the paperwork on these clips, again, go to ESR reports or other paperwork. In this particular clip, it says 4 clips per fixture required for the UL listing. So to meet the requirement of 41016, you have to have 4 clips. So let's look at the code requirements. Light fixtures weighing less than 10 pounds shall have 1 wire. So this is going to be like your can lights. Light fixtures weighing between 10 pounds and 56 pounds shall have 12 gauge wires. And light fixtures weighing more than 56 pounds shall have positive attachment, and the wire shall be taut. But we shouldn't be too hard on the electricians, right? Because there's very little of this information that's in the National Electric Code, and the National Electric Code does not give you a specific direction to go to the ASTM standards that we've been referencing. However, that does not negate the fact that it still has to be complied with. So again, National Electric Code 300.11, A1 or 2, where independent support wires are used, they shall be secured at both ends, so they got to be attached tightly at both ends. And here's an interesting thing that quite often gets overlooked. Where independent support wires are used, they shall be distinguished by color, tagging, or other means. A lot of times I've seen jobs where they paint the wire green, or they put some kind of little flag on it. Sometimes it's just electrical tape or something. Again, that's a conversation that needs to occur between the contractor and the inspector. So continuing with the National Electric Code, Article 314.23, enclosures within the scope of this article shall be supported in accordance with one or more of the provisions. Typically, this is going to be requiring that you have to have the clips, and you also have the additional support wires. And part of the intention of all this is that we don't want these light fixtures dangling down and hindering egress of the building. And equally important is hindering ingress by firefighters. They don't need to have energized, light fixtures and stuff falling on their heads and creating hazards that are just not necessary. So now let's address a few issues with HVAC mechanical systems. In seismic design categories C and D, we're going to have requirements in the ASTM 580 that apply. Typically, this is mechanical services less than 20 pounds must be positively attached to the suspension system main beams or to cross tees with the same load carrying capacity. So typically what we're talking about is these registers that we're going to see, especially on Z-ducts and stuff like that. We want to make sure that they're properly attached. Again, we're trying to keep these things from falling down and hindering egress and egress. Code requires that these registers be attached. Usually it's one attachment on opposing corners, so a total of 2 is all you need. This is a photograph where actually we're just lifting the register straight up off the ceiling grid. We also must consider fire sprinkler systems in these drop ceilings. For seismic C, the minimum 3/8" clearance is required where these sprinkler heads come down through the ceiling grid. Now, for seismic D through F, for ceilings without rigid bracing, sprinkler head penetration shall have a 2" oversized ring, sleeve, or adapter through the ceiling tile to allow for free movement of at least 1" in all horizontal directions. Flexible head design can accommodate 1" free movement. And again, this is an engineered design. Again, flex head or flexible hoses have their own unique requirements. You're going to have the manufacturer's installation instructions with these as to what extent they can be looped or kinked or anything like that. Typically, they can't exceed 6 feet, but again, it's going to go by an engineered design on these flexible sprinkler hoses. And here's a good example of what can occur over time, right? As things kind of settle and the building moves and finds its own level. When you have rigid piping, you can actually end up with the sprinkler heads that end up above the ceiling, and therefore they become ineffective in case of a fire. All right, so let's touch on a couple other issues as we wrap this up. So we're going to kind of extend this a little bit beyond just the ceiling grid because we're looking at above ceiling inspections, how I'm looking at this. So I want to touch on the roof decking issue. We have metal roof decking on a commercial building, and it is the roof, not a floor above. We need to be looking real close at Article 300.4E, where it says cables and raceways installed under roof decking. A cable or raceway type wiring method installed in exposed or concealed locations under metal corrugated sheet roof decking shall be installed and supported so the nearest outside surface of the cable or raceway is not less than 1.5 inches from the nearest surface of the roofing deck. We see this quite a lot where EMT is run right up against the roof deck. Now, there are some exceptions if you use rigid metal conduit or intermediate metal conduit, but for MC or EMT, you cannot be within 1.5 inches of the roof deck. So here's a decent picture just showing the what we're talking about here in the code. And here's an actual photograph of what I took on a project one time. You can see the EMT is run tight up against the bottom of the deck. And the screws you see were long enough that they could actually penetrate that. But fortunately, they didn't get over that far with their screws. Seems like these roof decks are attached with 6-inch long screws that are very, very sharp and able to penetrate just about anything. So this is something to watch out for. Cable trays and electrical conduits shall be independently supported and braced independently of a ceiling. They can't depend on the ceiling grid wires, and nothing along the lines of conduit or MC can be attached to the actual ceiling grid wires. So let's talk a little bit about a unique situation. That's plenum cable. The National Fire Protection Association, NFPA, has recognized the potential of a hazard that's created by wire and cable in an environmental airspace. All following NEC editions have requirements for this. The National Electric Code states that all cabling not in conduit installed in plenum spaces shall be listed as having adequate fire resistant and low smoke producing characteristics. Typically what I'll see in a plenum is a data and comm cable that needs to be looked at very closely to make sure it's rated for plenum use. And we mentioned this earlier, but IBC Chapter 17 Special Inspections, non-structural components. This is your ceiling grids. So if you go to 1705.13.2, the building official, the authority having jurisdiction, can require on a commercial site, on a large construction site, that special inspection be done for the ceiling grid system. And this is probably a good method to consider. So here are a few additional websites that you might want to go to just to expand your knowledge on ceiling grid systems. I hope this information has been good for you, and if you'd like to get a copy of a checklist that I've developed, just go to the description and you'll find a link there. You can get to my email address and ask any questions. I'll be glad to send it to you. It's free of charge. I do ask that you subscribe, like, share, and if at all, support this channel. We really do appreciate all of you, and we hope this information has been helpful for you.